ways, and the one thing that I'm going to focus on, because it's a quite efficient way of getting mergers and collisions happening, is by having these systems make a transition from one dynamical regime to the other. So I'm going to start out with those triples that you saw earlier that are dynamically stable, where we have two orbits, and they're going to move towards a regime where they are not stable anymore or less stable. And Carl already knows what's going to come, which is a movie from Carl. So this is the type of reaction that you would expect in this regime where the systems are not dynamically stable anymore. So you start with a binary, and Carl shot a third star at it, and you get this beautiful interaction, very chaotic behavior, and I'm just going to let you watch and enjoy. Yeah, there we go. So these are the type of reactions that you would expect to find in a stellar cluster. And what you see here is that the system dissolves in a binary and a single star. And in this case, the star that becomes single is one that was in the binary previously. So there's an exchange of the stars. And something else that can happen is that this binary that's left over could be more compact, so that it can merge later on in its life, or either even merge or collide during this interaction. So these are the systems that you've seen previously, the systems that become dynamically unstable. But the question that I haven't answered yet is, how do these systems, I do it again, how do these systems become dynamically unstable, or why? And where is that boundary between stable and unstable? So just to give you a bit of a hand-waving feeling, this is the stability limit, just one of them. This one is from Rosemary Martling and Sverre Aanset. And what you can see is that the system becomes more, less stable if the outer eccentricity is high, or if this ratio of the semi-major axes, if that becomes closer to unity. So if the two semi-major axi approach one another, the system is less stable. And that is a trick what's happening here, and it has to do with stellar evolution. So this always sounds very complicated, but really just bear with me. It sounds complicated, but it's not. So if you have a binary and one of the stars loses mass in the wind, what's the effect on the orbit? Well, if it's an adiabatic effect, the orbit widens. How much does it widen? Well, that depends on how much mass you lose. And to be correct, the relative amount of widening depends on the relative amount of mass loss. Now the inner binary has two stars, so relatively it's losing more mass compared to the triple as a whole. So that inner binary is relatively widening more than the outer. So these two orbits start coming closer to each other, and this is how we can drive a triple that used to be stable over the stability limit and make it unstable. So we're finding that that happens about once or twice every 1,000 years in the Milky Way. A fraction of them will lead to a collision during that interaction, during the cool movie from Carl. And that gives a rate of about 1 every 10,000 years. Interesting thing is that this would be the highest rate of collisions in the field. Normally when we think about collisions, it's the stellar clusters, but this is a way of making them in the field as well. Another way of making our triples unstable is by having a supernova kick. Now of course when I'm talking about supernova kicks, I'm talking about more massive stars that collapse to a black hole mergers equals gravitational wave sources. So the channel here that I'm thinking of they look like this. So I'm starting with a triple that has 3 massive stars. Using my code, I'm simulating the evolution of those systems until I have 3 black holes. Now, some of them are going to disrupt because of the supernova kick. Right now I don't care about them, and I ignore them. Some systems might have mass transfer, also interesting, also for the future. Right now I'm only focusing on those that give me a triple black hole. And because of the supernova kick, the system now makes that transition to a different dynamical regime, where mergers are more likely to happen, where the eccentricity variations are very strong, and then the merger is more likely to happen. The rate that we're finding for these systems at solar metallicity is about 1 per year per gigaparsec cubed. And if you go to lower metallicity, Carl and Fabio showed that the rate goes up by an order of magnitude. So these numbers are comparable to the rates that we expect from stellar clusters. It has there's one distinct characteristic that I want to mention, which is the eccentricity. So this is the eccentricity of the systems the moment they enter the LIGO band. So in blue and red, you see the classical channels of getting a binary black hole merger from isolated binaries and from clusters. And in black, you see the eccentricity distribution from our models. And you see that it's orders of magnitude higher, but it's still pretty much 0 for LIGO. 10 to the minus 3 is still not observable. But if you go to LISA, then this eccentricity would be observable. The side note that I want to make is that these simulations of clusters do not include secular evolution for the triples, nor do they include the higher PN terms. And if you do that, then also a fraction of them will have higher eccentricities. So with Daria and Carl, I want to chat today and see if we can come up with something else that can distinguish these two channels from one another. The other thing that I want to mention is related to the inclinations of these systems. Because if we want to get a merger, you need a high eccentricity. In order to get a high eccentricity, we need a high initial inclination. And this is what you see in this plot. All of our systems that are finally merging in red are very much biased to an inclination of 90 degrees. On the other hand, my full population of triple black holes have an inclination distribution that pretty much avoid that area. And the reason is that if you have this high inclination very early on in your evolution, you're going to interact when these stars are still stars. So those are losing. So I think it is important that we take into account the stellar evolution of these systems before we get the triple black holes. Now, we can do the same game, not with black holes, but with white dwarfs, right? And get more white dwarf mergers. And we can go one step further and demand that this eccentricity is even higher, so that the white dwarfs in the inner binary are put on a collision course with one another, because then we get collisions between white dwarfs. And the reason why I'm interested in that is because they have been suggested as supernova type 1a progenitors. So type 1a's hardly need an introduction, but I do feel a bit obliged to say something. So I'll just mention that they are one of the brightest cosmic explosions. They have been very useful tools in cosmology to measure distances, as well as the expansion of the universe. And they're also responsible for the majority of our iron peak elements. The big problem with supernova type 1a, which introduces systematics in our use of using them as a tool for measuring distances, for example, the big problem is that we don't understand their progenitors very well. There's a consistent, or not very well, not at all. So there's a consistent an agreement that it's likely a thermonuclear explosion of a white dwarf. But how do you get a white dwarf to explode? Now, classically, there's two families of type 1a progenitors. And in one on the left, the single degenerate, it's a white dwarf that's accreting from a companion star. And on the right, it's two white dwarfs, so double degenerates, that are merging. And classically, if they reach the Chandrasekhar mass, they would explode. There's also a variety of other models that are extensions, combinations, completely new, that I don't want to go into right now because I don't have the time. Just want to mention that for these white dwarf collisions, they have one very nice aspect, and that is the detonation mechanism. Because in these other channels, the detonation mechanism is not very well understood. We cannot resolve it, which means that we have to introduce free parameters to model it. And in this scenario, it's the collision itself that brings the detonation, which is just very elegant and cleaner in a way. So again, I did a simulation. I took, I think 7 or 8 different models for the triples, evolved them in time, and tried to estimate how often does this happen. So the type 1a rate from OR is about 10 every 10,000 solar masses of stars. From this accreting white dwarf systems, my models predict about 1. And honestly, this can go orders of magnitude below, depending on the white dwarf accretion physics. For double degenerates, I find a rate that's a little bit higher, but it's still on the low side compared to observations. And then for the triples, I'm finding a rate which is this. So this is, at best, 3 orders of magnitude below the type 1a rate. So I think it's a very interesting channel that could give rise to some supernova type 1a, but I find it hard to see how this channel could lead to the majority of the standard supernova type 1a. I think this channel is just too specific to give such a high rate that we already have a hard time doing with just binaries. Yeah.
Can you just, so that it's clear in our minds, can you explain exactly what this particular triple model was?
Oh, okay, yeah.
Because there are many different ways to approach it.
Let's go back. So I'm going to start with 3 stars. I'm going to start with my triple. I'm going to evolve that in time until I have 3 white dwarfs. There's no mass transfer. They don't become dynamically unstable. We just get a stable triple white dwarf. And if that